Thank you guys, another good day. Welcome to our live classes. It's about to start. If you have not joined, just join, subscribe and comment. Please share with your friends so that we can have a greater movement. Thank you guys, join my classes. Thank you, welcome all. Today we are going to discuss our better part of the generation system, that is the hydro generation system or the hydroelectric power system. Remember we gave an overview and I also demonstrated using a sketch of how all this works. If I could show you a little bit of it. I gave this sketch over here, so I tried to highlight the different procedures that we have in power hydroelectric generation. So I also gave these steps and also gave the illustration using a diagram. We saw a river being a dam being built across a river. Then we saw this water being led through a channel or a penstock up to a point where it hits the turbine. And then from there we have the generator converting the energy to electrical power, and we have transmission up to where we have the substations in the different localities. So today I want us to see how we can actually be safe while doing all that system or this procedure of power generation. So like my page, let's see. Remember you can follow me on my handles, the Food Engineering Solutions, and let's learn together. Do this in large scale. I illustrated last time about how this is done. Today I will be giving you a good lesson of the safety we take and also show you what is basically done using a schematic. So here guys, you can see here I have my hydroelectric production. So what basically happens, you can see this is a reservoir. This is a very big source of water, maybe like a river or something like that. Thank you Didi for joining in. Remember, this is what I was trying to say, a river. It's I illustrated here using this diagram. So a river is flowing and then it finds a dam somewhere where it's blocked. You can actually see from this point, this is our dam here. This is our dam. Thank you Apostle for joining. When you have a dam, it will block this mass water here and create a lot of pressure. So you can see this water here is directed using a very big pipe. As we said yesterday here, you can see this pipe is called a penstock. Thank you Faima for joining. It's called a penstock. This penstock is what directs water to the turbines. Now you can see here this penstock comes, this is a down wall, a very firm wall that cannot be broken by this water here. So what happens, this water comes to the propeller here, and after that it is released back to the river to continue with the flow of water. So what happens here, it is these turbines which are turned by the mass water which carries a lot of pressure with it. Then from there it rotates this shaft here, and then this generator here, which now converts mechanical energy to electrical energy, now does its work perfectly, after which it now produces power which is taken to the transformer here. So you can see this procedure is very simple, just as I tried to explain yesterday. So our issue here is simple and there is no rocket science applied. So today guys, I want us to see which are the precautions that we take when building this power generation station, and also which sensors do we use in here so that we can have a clear, safe and smart flow of electric power. So let's start with that. Remember, you can join my page. You can like, you can subscribe. Thank you very much everyone who has joined in. So today we get to the safety of hydroelectric generation. Thank you Watu TV, thank you very much for joining. So what we do here, we actually take every step in this production of the power and see what risks could actually occur when we are producing this power. One and the first obvious assumption is, what if the dam breaks? So we consider the strength of dam. Thank you Ian for joining. Strength of dam means this wall, you see, this is called the dam wall. Remember, the water itself or the water body is not the dam. The dam is this wall. So what happens, we tend to create a wall that is able to block all this massive water. That is by having the wall wide and thick enough on the bottom side of it. You can actually see this wall, the dimension from here up to this point is thicker than from here up to here. So what there is that pressure accumulates at the bottom of every vessel. So at the bottom here, we need to have a very thick wall that will hold the pressure. Actually, it's assumed to be thrice the pressure that is on top here. So the first precaution is strength of the dam. So that is our first point here. So our second point we should consider is the strength of penstock. Penstock is this big pipe here that actually carries the flow of the water. If this penstock is weak, actually it may burst in between, maybe here, which may cause eruption of water and overflow at this area. That is a very big risk and it can cause a very big calamity. So we don't want that. That is another thing to consider. Then we need also to consider the rate of water flow. What I mean by rate of water flow is the rate of flow per second through this pipe. This pipe is designed with a given dimension, maybe let's say 3 or 4 meters wide in diameter, such that it won't break this point of the turbine. Remember, this turbine has its own strength and should not be broken just like that. So we must try and avoid any breakage that could occur here due to overflow of water or due to maybe any kind of eruption of this penstock here, of which could carry debris to this point and hence damaging the propellers or the turbine. So that is another thing to consider. Then number 4, we also need to consider the positioning of turbine. Positioning of turbine means we don't want actually our water to hit this turbine directly. We want this water to hit our turbine from such an angle that it will spin. So I can actually draw a very simple illustration here. If this is the water flow like this, if we have our turbine maybe somewhere just beside this water flow, it will actually hit these two fans here. So it will actuate the spin to this direction. If my turbine, let's assume that's a sketch of the turbine, is hit directly by this water, it will not have a distinctive direction. It will try to move like this or like this, which will break this turbine. So the position of the turbine should be considered. The other thing is the flow back of water. Remember, this water should come, get in here, rotate our turbine, then get back to the river and continue flowing. So this outlet here is very important to consider. So we can actually put our point number 5 as outlet diameter. If you build a very thin diameter here, this water can accumulate and actually overflow in your generation station powerhouse. So we don't want that. What we do, we actually consider the inlet at the outlet diameter to be such that they are almost the same flow at the same rate of water, but they should actually give the water a little space to create force of rotating the turbines. So with this said, guys, we can actually separate these precautions or these factors and then now go to the electrical part of it. Remember, that is the physical part of it, at the geophysical impact of the factors. But now we are going to see how this transformer here and this generator here and these transmission systems, how we actually make sure they are safe. Remember, we can actually have two spaces there. So these are the safety for hydroelectric generation. Now we go to the electrical part. First, we need to have a steady power flow. This is to ensure that we have power supplied to these consumers without any hinge. That means we must produce our power here at a very reliable rate so that it gets here safely and at the safe rating. So what we consider in this basically is just things to do with voltage, current, frequency, and actually power itself. That is, power is a result or a multiple of voltage and current. Now times the power factor, of which is cos phi. So here our main aim is to produce power at a constant voltage, constant current, at constant frequency, and according to the power demand. That is why I have included power in this electrical safety. So we have to make sure we have steady power flow. Based on that, we don't need to actually go on the safety of transmission, because that is majorly about maintaining the transmission system. Afterwards, we are going to see how we actually maintain all the safety we put in the transmission system lines, so that we have a safe consumption at the consuming end. So one of the things that we must consider here is voltage. Voltage is what is considered to be the primary product from a generation station. So voltage is actually monitored using voltmeter. So in our generation station, we need a voltmeter. Where do we actually place a voltmeter? If we have our generator here, remember we said we produce at in form of delta power supply. So if we have our generator here, in order to monitor our voltage, we must take this point, at this point, at this point. If we take our voltmeter here, it should give us a good reading of the outgoing power, like this. If we take our voltage here, it should also give us a good voltage reading about the power going out. Remember, these are three-phase supply. Delta. Delta means it's a phase-to-phase generation, red, white, blue, at an angle difference of 120 degrees phase difference. So if you look at our diagram here, after now we have managed to overcome all these challenges and the risk that may occur with the physical design of the generation system, we can actually be able to monitor our voltage coming from this generator. How do we do that? That is why we have created a powerhouse here, so that we can accumulate all these gadgets here. So basically what we need is to create a digital voltmeter where we can be monitoring constantly the output voltage from our generator. Remember, if you have incoming voltage like this, at this voltage maybe 3-phase, maybe it's 3 kV approximately, but it can vary. Maybe let's say it's 3 kV equal to we can actually come here and apply our gadget on this point. Here you can have a regulator like this. Regulator is for regulating this voltage to a constant value. Maybe if this is 3.5, no, 3 kV up to 4 kV, Here we have 4 kV or 3.5 kV or 3 kV strictly. Not all of them, just one of them. So this is unregulated. Output here is regulated. So if we have unregulated power here, we can actually place our voltmeter on this side, maybe somewhere here, and then we place a regulator here, there, and then here we have our another voltage. So what I'm basically saying is, if you have this voltmeter like this, here we have regulated power like this. So unregulated power monitored through the regulator, monitored, then regulated. So if we have a screen here, a computer, we can actually take this reading and bring it there. We can actually take this reading and bring it there to this computer. So we can be able to monitor our voltage from this point. Now before releasing it to the consumer. So that is voltage regulation. We go to current. Next thing is current. Current is measured in amperes. Remember, after producing our voltage, we need current to be steady. Steady flow of power means there is current, steady flow, and voltage, steady flow. That means our current, if we have our source or the generator there, we can actually have our current being monitored using something we call current transformers. So these current transformers do not come into direct connection with the main power. Actually, when we have a main conductor like this, power going through like this, our current transformer must be going around it like this without actually connecting to the conductor of the main power like this. So here actually we have a coiled rod, and then we have power like this, coiled rod, and then output. So in our current transformer we have two outputs, and that is AC, common, and A1. So this means the current that flows through this conductor is induced to this transformer, and the current here, there will be a voltage induced current like this. So here, if we have our power flow, high voltage, and then here also coming out through this So it means there will be induced current to this. So if we take these two wires here and actually put an ammeter. Ammeter is instrument for measuring current. Ammeter. So we place it between this point, it will give us the reading. So to make a clear illustration, I can have a diagram like that. Then I can have a conductor, let's say, is coiling like this. Like this. So if we place an ammeter here, and then we put current here like this one will give us a reading. So what we do in this generation station, we place ammeters here, and then we take the reading of every phase. So ammeter, ammeter, ammeter. So these three ammeters will give the reading for every phase here. So you can actually see we can be able to monitor our three phases if we have a screen here, maybe a computer. Then we have our current transformers like that. We can be able to give each ammeter coming to this computer here like this. So each ammeter is current transformer, current transformer, current transformer. We can be able to monitor all these currents from this computer. We can call it as a digital ammeter because it can record current. So then we have power. Remember, we said power is a product of voltage and current times power factor. So power factor in this case is considered to be mostly 0.8, but this is instrumentally corrected by the PLC itself. So we need to have a correction of voltage and current. So in power, we tend to have our current and voltage multiplied together. So our gadget here, that is called the watt meter. Watt meter because it reads power. This gadget is able to read current and voltage at the same time. So if we have our three phase like this, then we have watt meter like this. We can actually connect it to a computer to give us the power in kilowatts. So we need to correct power using a watt meter. A watt meter is a gadget used for making sure we have steady power flow by monitoring. Current, we need ammeter to make sure we have a good steady flow of current. Remember, ammeter is a gadget used for monitoring current in amperes. Then we have voltmeter, is a gadget used for measuring voltage. and we use it to make sure we have steady flow of we have explained. So I will now let you know what is important to do when we have a case of any of these going faulty, or if in case we have any abnormal condition. Now we can first finish with the frequency. Remember, we have talked about voltage, current, power. Now we have frequency. Frequency is the number of oscillations per second. This means how many oscillations of power do you get in 1 second. This means if we have t equals 0 and here we have t equals 1 and this one is in seconds, and we have voltage here, then remember we are producing AC, so this power goes like this. So how many in 1 second between T0 and T1 do this happen? So here we have 50 Hertz. So this power should oscillate 50 times in 50 times per second, like this. So we have in our generator the shaft rotating like this. It has something called tachometer. This is gadget used to measure speed. This is rotation of generator per second. So this is how we monitor frequency using a tachometer, but the tachometer is not used to measure hertz in the power system. It's used to measure the number of rotations in the generator. We have things that we call frequency sensors that are used inside now the power lines. Frequency sensor. So with this said, now we can try to see what happens when we have any abnormality. Remember, we started with the voltage. So in case there is over voltage, one thing you should check is the generator itself to make sure it's not overspeeding. So in case of, we can have a new page. In case of over voltage, we need to check speed of generator like this, which could be of course be caused by excess flow of water or a faulty speed governor. Remember, in speed we use governors for speed control. In case of overcurrent, we usually check on things to do with CBs or air circuit breakers, so that we know why they are not tripping on the rated current. In case of over frequency, we check speed of generator as our primary fault. So with this said, actually you can be able to compare the opposite. In case of under voltage, check the AVR of the generator so that you can actually see the speed is reached by its command from the AVR or the governors. Then if we have a undercurrent, you should check if the generator is producing enough voltage fast. If in case of speeding, that is when you have over frequency or high frequency, and we should use speed governors or monitors for standardizing the frequency. Nowadays there are inbuilt frequency monitors that are able to generate the command on their own. So with this said, we are going to have a lesson of how we transmit from the generation station up to the substation and any load in between, the transformer, that is the step up in the generation station, and the substation. But we can actually try to trace and see what should be done in case of the total blackout in the generation station, because remember, we cannot just open this gate and let this massive water flow when this thing is stagnant. That brings us to another interesting area where we have starting a hydroelectric plant. Remember, our generator here has these turbines. We cannot just put water and just let it flow at once through this pipe. We need to have a clean and a smooth acceleration of this turbine to avoid breakage. So we have a gate. This gate is operated using motors to raise and lower the upper part. This is movable part, this is non-movable part, so you can raise and lower this point. So we need to have a steady flow of water so that we don't break the turbines. With that, we have our system here, the starting system. Here we can have generation station 1, generation station 2, generation station 3. These generation stations are interconnected with power for enabling cool or soft start. These generations have transformers. The other generation has its transformer, and the other generation has its transformer. So what there is, each generation station has a system like this, and now we need to have a smooth start. So in our turbine, if this is our turbine here, like this, if it's rotating like this, we have a generator here with coils, which now produces power. So this is generator. Remember, this generator needs to have a smooth start so that it can have smooth power. So what we do is we add another winding to the shaft of this. We have a second operation coil. Remember, this shaft is free through the generator and also through to the turbine. So we have actually another small winding mounted here just to create an electrical motor, some kind of electrical motor which helps in starting this thing to rotate. So when this power from the transformer is fed to these windings here, they actually help to start rotating this thing softly. Then from there, we actually open the gate. After the spinning has started, we now open the gate slowly by slowly, of which now to make this turbine spin at its maximum speed. So the other two the same. If this is the winding for the generator, then we have shaft and the turbines. Like this. Here we have this. So this transformer provides power to these windings that now helps to start this turbine smoothly. Before now we can open the flow of water to continuously turn this thing in full speed. So assuming that in this generation station 2 we have power blackout and this thing has to go on, what do? We actually tap this power from this source that is interconnected through the 3 stations, then put on this induction power to this coil, after which it will start to turn this turbine like this. Then we open this flow of water at full speed to maximum speed for this turbine. So that is how we have a soft start, or if your generation station has stopped, that is actually they turn it on without breakage or safely. So with that said, now we can have another class of taking a step from where we have transmission, that is from the step up transformer, and then we see what happens in between here from the stage of step up transformer up to where we get to the final consumption. We will see what happens in between here. We see why these poles are built like this. We see why these safety gadgets are put. So if you have a question of this lesson, let me know. If you want to if you want me to clarify about any step from the water flow here up to the step up transformer here, let me know. So thank you very much for enrolling to my class. It's free of charge. Make sure others follow, make them invite them, and let them know there is something like this happening. And I will be giving you a highlight of our next unit, but we are almost halfway done with the hydroelectric generation. Next, I will be taking you through the next type of power generation. Let me just give a hint and say if it's not geothermal, we can go to solar or something like that, but I prefer we start with geothermal because it's it's closely connected or related to this hydroelectric generation. So if you need to know more about this, you can actually visit my page, Facebook, YouTube, TikTok, and like, share, subscribe, and comment. Wood Engineering Solutions. You are gonna find these lessons there. So thank you for following up my classes. If you are not early for our class, or you just joined us late, I'll be posting this video and you'll be seeing what we have learned. And if you wish me to handle a topic that you feel you really need to have it, please let me know. So thank you very much. If you need me to illustrate and go deep about all these sub-units we have learned about frequency, power, everything, you can actually see, and I can go through it. Thank you for following up my classes. Subscribe to my YouTube channel, I'll be there. Then I have something more. Last time we learned about the connection of this gadget. It's called a power contactor. This is totally separate from what we are learning today. So this is called a contactor. I showed you how it's connected, and I gave you a simple experiment of it. Now I'll do another short video. I will show you how we connect the other type of contactor. That is the manual operated contactor, and see how we use these gadgets. I will also show you how to connect them, so make sure you follow up. Thank you very much, whoever has joined in. I will be giving you such live classes as we have had. You can see we have done the hydroelectric. Next, I'll be giving you things to do with geothermal power generation or solar, whichever comes first. But we are going to finish first with the hydropower generation, and that is the transmission part of it. Thank you guys for joining in, and I really appreciate your time. So if you feel like you need a special clarification about any subtopic, any unit, any subtopic you feel like you are not present and I need to repeat, I'm here for